Okay, guys, we're going. Shh. Quiet, please. All right, so today we're going to analyze graphs of polynomials. So we're going to do some stuff today that's going to seem similar to what we were doing back at the very beginning of this chapter in 4.1, talking about properties of polynomials and that sort of thing. But we're going to focus on some features of graphs of these things.
Yeah, it's 4.9.
It's 4.8 actually, because we've had to move things over a day. Okay. Shh. So, three things that we're going to be looking at specifically. Specifically, the three things we're going to look at here are zeros, turning points, and increasing and decreasing intervals on a graph of a polynomial. Okay. So what I'm going to do first is I'm going to just draw you a graph where we're going to do this, and then later on we will go on the calculator. So if I give you an equation of one, you can graph it on your calculator and do all the same stuff. And I'll show you where you need to go on there to do all of that. Okay. So let's take a look at one that I'm going to draw by hand here. Okay, so let's say we got a polynomial like this. And I'm going to just mark some key spots here. So let's say this is at -2, and this is 1. This is at 1, 3. Maybe this is at 1, 2, about 3. Here we've got, let's say 5, and this is -2. And then right here we're at 7. Okay. So, first things first, something we've done before. If we're looking at a graph, where do we identify the zeros? Raise your hand. Yes, Jason. Okay, so where is that at? Bless you. 3 and 7, right. So x equals 3, x equals 7. Now, when we're talking zeros, these are what kind of zeros? Real zeros, okay? Ones that you find on the x-axis, those x-intercept, those are real zeros. Now, we don't know what the imaginary zeros are on this one, but we do know how many we have. So let's start with this. Take a look at the shape of this thing. Can anybody tell me what the degree is of this polynomial? But just by looking at it, yeah. It's not a 5. Yeah. It's not a cubic. Yeah. It's to the 4th. Okay, so think about this for a second. One thing that we've talked about before was end behavior. If they're both going the same direction, in which case this one they are, then the degree has to be even, right? So it couldn't be a 3. Couldn't be a 5, right? It has to be even. But how do I know specifically that it's 4? Is it just a lucky guess, or how do we know? So it's something that we haven't talked directly about, but it has to do with how many of these little curves there are in here. Okay? You can count it by how it curves. So 1, 2, 3, 4. So it's a degree of 4. Okay? Another way that you can identify that is we're going to talk more about these in just a minute, but these points here, here, and here, these maximums and minimums that are in there, how many do you see? 3. The degree is always one more than that. So there are 3 of those, so the degree is 4. What?
Remember that example on our homework where it looked like flat bottom, but it would still look like quadratic?
Oh, to the 4th? Okay. So this is not... How can I explain this? If it's a nice smooth curve and you don't have any of those weird little like flattening out spots or something like that, then you can just rely on the curve to count what it is. So with something like that, like if I had something like that in here, so if I had one of these would be looking like a little parabola, like a parabola. But if this came down and like flattened really a lot right here, and then came back up, then we'd have almost kind of like a double root type of a situation where the degree would be a little bit more then because of that. But I don't want to confuse you guys too much. I'm going to be just sticking with ones that are nice, smooth, none of that weird kind of stuff happening on there. But you're right. This is not every single polynomial does this. That's not true. But in general, if it's a nice, smooth, nothing funky happening on it type polynomial, you can rely on that. Okay? So, yeah, so the degree we know is 4. So if the degree is 4, how many imaginary zeros would this have? 2. Okay? It's got those 2 real zeros, 3 and 7, and there are 2 imaginary zeros. I don't know what they are specifically because I don't have an equation to go find them, but I know there should be 2. Because remember, the total number of zeros is supposed to match the degree.
You know they're imaginary because you don't see the other points.
Yeah, because I know the only real zeros are 3 and 7. That's it, because those are the only x-intercepts I see. So, yeah, there's going to have to be 2 more, and they have to be imaginary because they're not real. So, okay, so that's doing zeros. Let's talk about these turning points that I mentioned. So a turning point, also known as maxes and mins, okay? There are 3 of them on this graph. Here, here, and here. And each one of them we can identify as either being a maximum or a minimum, okay? So, can you guys give me the coordinates here real quick that I can write down then, what you see on the graph? So, coordinates of a turning point. -2, 1. 1, 3. Shh.
3, 1.
And 5, -2. Okay, now, like I said, each one of these can be identified as a max or a min, but we actually technically call them local max and mins. Okay? And what I mean by local is, like, around that point, it's the lowest thing around or the highest thing around, but it is not necessarily the highest or lowest point on the entire graph. Like, for example, this point right here, you guys see how that's a minimum? Okay? It's down kind of in a valley right there. Is this the lowest point on the graph altogether? No. So it's not the absolute minimum. It's just a local minimum. So locally, around it, it's the lowest point. Okay? If you see a little valley like that, it's a local minimum, not necessarily an absolute minimum. So we're not going to worry about is it just local or is it absolute and all of that, but just tell me if it's a max or a min. So this one is a min. The 0.13 would be a max, and 5, -2 would be a min. Okay, so those are our turning points then, our maxes and mins in the middle there. Okay, what you would say is this one has a local maximum at 1,3, but has no absolute maximum because it keeps going up. You can't get to infinity though. So that's not a maximum. When you get there, you let me know. All right, anyway, so once we know our turning points, then we can start identifying some increasing and decreasing intervals. Okay? So if we look at the graph, you guys know what I'm talking about when I say that? Increasing versus decreasing. So as I trace this with my pencil, tell me what I'm doing.
Decreasing, increasing.
All right. So hopefully Claypool cleared that up for you. But everybody got that? Where I'm increasing, where I'm decreasing on that graph? No, I'm not going to do it again. So as you trace it with your pencil, going left to right. As you go down, that's a decreasing interval. As you come back up, that's increasing and decreasing. So what I want to know is when we're describing these, it's from what x value to what x value is it doing it, okay? Liz, question?
So you said once we know our turning points, we can find what?
We can find the increasing and decreasing intervals. Okay, so can somebody then identify for us at least one increasing interval?
I'm guessing from negative 2, 1 to 1, 3, those points? Did I say that?
Yes, you just want to use the x values though. So you would say from negative 2 to 1
All right, got it.
is an increasing interval. Okay?
So would it
Yeah.
be like negative infinity to negative 2?
That's decreasing.
Yeah, add the
Yeah. Yep, we'll get there in a minute, but you're right. Okay, so increasing intervals, negative 2 to 1. You guys have all seen that kind of notation before, right? That's an interval from negative 2 to 1. X is in between negative 2 and 1. Okay, so look at the graph. There's another increasing interval. And somebody else who has not spoken yet, tell me where that is. Yeah?
Would be 1 to 5.
Be one. That's decreasing. We want another increasing one. Because this one, from 1 to 5, I'm going down. So where's the next increasing? Not you got it? You got it?
It's 5 something, I don't know.
Yeah. So it starts at 5 and keeps going, right? So 5 to infinity is how we would say that then. Yeah, because it doesn't stop. Now watch how I do this interval, guys. If I'm going to do 5 to infinity, I could either do it like that, or I could just simply say x greater than or equal to 5. Either way, if you do it like this or like that, it doesn't really matter. Now, the first one, though, notice how I didn't put an or equal to here? Because you can't equal infinity. You're never going to get there. So, yes,
You already
yes, I
said
do.
this and you still haven't got there.
I will dedicate my entire life to finding the number.
Okay.
Start now.
Infinity is a word that says.
Okay, so
How many times do we know?
decreasing. Can somebody give me a decreasing interval in here? Somebody has not answered anything yet. Mr. Kukels. Mr. Kukles.
Oh, it's calling on me. Okay.
Yeah.
Would it be 1 to 5?
1 to 5. There's a good one.
Could you go like, thanks, Steve.
Well, you have to make sure that when you do an interval like this, the small number is first and the large number is second. So, 1 to negative. No, you can't. You have to trace it left to right. So this is decreasing. This is actually increasing because it's over here going this way. All right, now there's one more decreasing interval in there. Somebody else? Yeah?
Infinity to negative 2.
Okay. Except it's negative infinity technically. Up to negative 2. Or, you can simply just say x is less than or equal to negative 2. So again, either one of these is an okay way to write that. But yeah, so for this particular function, there are 2 increasing intervals, there are 2 decreasing intervals. There you go. But you're using those points from the turning points, the x values of those turning points, to help set up where those intervals start and finish, right? So that's important. So the next one we're going to do, we'll look at a graph, and we're going to do all the same stuff, except we're going to use the calculator to help us figure out where some of these points are. So I'd like you to type this into your calculator, if you would. Uh-huh. So we got 6x to the third plus 5x squared minus 17x minus 6 And I'll even give you the window that you need to use to see it really well. I know it. Okay, so you can type that into your y equals, and then set up your window with those mins and maxes, and then hit graph and take a look at this thing. You should see this nice, beautiful cubic function on your calculator after you do that. It'll be amazing. Double check it. It kind of is. All right, so if you got everything in there correctly, should look something like that. Awesome. Okay, so we're going to do all the same stuff. We're going to look for where the zeros are, those x-intercepts. We're going to look for where the turning points are. In this case, there are 2 of them. And then we're going to use the coordinates of those turning points to figure out where the increasing and decreasing intervals start and finish. Okay? So, when you do this, we're going to be going through this menu where you hit second, and then the button that says trace right here. And in there we have this calculate menu. Question? Very quickly, yes. All right, so first thing we're going to do is 0. Yep. And so it's going to take you back to the graph. And down at the bottom, it's going to say left bound, and it's going to have some coordinates on there. All right, we've actually done this before. It's been a little while, but we did this way back with quadratics, looking at some graphs. But if you move this little cursor, we're going to look for this 0 over here first, okay? So it says left bound. What it means by left bound is you have to give this thing a left bound and a right bound. Basically, you're going to give it a little window to search in for a 0. So you have to go a little to the left of where you think it is, a little to the right of where you think it is, and then it's going to look within those 2 numbers, in between those 2 numbers, guys. So you give it a left bound, you give it a right bound. It's going to search in between those 2 numbers for where the 0 is, okay? Because there's more than one 0, you have to make sure that you're just going around one of them and not more than one, because then it'll get confused about which one you want. So my cursor, do you see how right now I'm just to the left of where that 0 is on the curve? Yeah, we're talking just to the left along the x-axis of where that would be. So hit enter for that, and then I move this thing a little to the right of where the 0 is. Hit enter again. And see the little triangles up at the top? That's telling you I'm going to search within these 2 spots. I'm going to look on the x-axis between those 2 numbers and try to pinpoint where that 0 is for you. Now by eyeballing it, it looks like it's going to be somewhere in the neighborhood of -2, right? Let's see exactly where it is. Hit enter one more time, and then it'll actually look for it, and there you go, right at -2. Okay? So we've got one of our zeros then, so we can jot that down now. So x equals -2. Okay, so let's jump back in here. And then we got to repeat the process for the other 2. So back into the calculate menu, go down to number 2. And then we'll move the little cursor again. Just to the left of the next one. Enter. And then scoot it just to the right of the next one. Hit enter. Enter one more time. Okay, so the second 0 is at -0.3 repeating. What is that actually as a fraction? 1/3. So -1/3 is our other 0? No, it's not 0.4.
I didn't think so, so therefore I'm right.
All right, so we got -2, -1/3. And then we got to go one more time over to the third one here.
1.5.
And yeah, it should be 1.5. And there you go, 1.5. So that as a fraction, I guess if we're doing all our zeros as fractions, that would be 3 over 2, but 1.5 is fine. Okay, so answer me this. How many imaginary zeros does this thing have? None. 0. It has 3 real zeros, but how many imaginary zeros? None, because it's a third degree and all 3 of the zeros are real. We just found them all. Okay, so we don't have any imaginaries going on. All right, we got the zeros. Let's go for the turning points. There are 2 of them. Yep. You see how we got 1 maximum and 1 minimum in there?
Now you gotta go second trace, and then maximum, left bound, right bound.
Yeah, so we've got, there's no like turning point option in this menu here. They do have minimum and maximum though. So you got to know which it is first, pick the correct one, and then go use it. So let's do the maximum first. So pick number 4. Okay, so the maximum, I got to move my cursor all the way over to where the maximum is. Okay, but again, I have to create a left bound and right bound. So I'm creating this tiny little interval around where I think that maximum is. So if I use my arrow to kind of go over just a little bit to the left, there's my left bound. And then move it just to the right of where that maximum is. There's a right bound I can use, and now it's going to search in there for the highest point. And that maximum occurs at the point negative 1.288522, 11.370406. Yes. But don't round too much. Okay? So you don't need to hold on to all those decimal places. So I would say 3. 3 decimal places is pretty safe for most things. Okay? So our maximum is at, if I do a little rounding here, negative 1.2, it would have to be 89 if I went 3 places. And then my y value, 11.370. And that we said was a max. Okay. I would like you to repeat that and go find the minimum doing the same stuff. Okay? I'll do the same thing and we see if we got the same answer here. And again, if you would, just 3 decimal places should do us well. All right, here's what I got. See if it matches yours.
Actually, that's exactly what I got.
Awesome. So 0.733, negative 13.412. Be sure that you selected minimum this time and not maximum. Otherwise, it's going to tell you the highest point in that little interval, not the lowest, and it's going to be the wrong spot. Okay? So first one, we had to do the maximum. Second one, we had to do the minimum. Okay? Just be careful of that. Okay, so now knowing where these turning points are, specifically, we can do all our little interval work again. Okay? You might want to look at the calculator screen at the graph to help you with that, to see where the increasing and decreasing ones are. So let's start with the increasing intervals. Okay, so looking at the graph, do you guys all see how there are two increasing intervals?
We don't really need the graph. Don't we just need the maximum and minimum?
Yeah, but I'm just saying, looking at the graph on the calculator will help you, though. Okay, it's a nice little visual aid. Yeah, you don't technically need it if you can just think about it in your head, but, you know, for most of us, this is going to be a nice little check. So, the first increasing interval, then, that we see would be from what to what? Negative infinity to what? Negative 1.289. Okay? All right, so let's jot that one down. Okay, so that's an increasing interval. And then, so where's the other increasing interval? Somebody who has not spoken yet, raise your hand and tell me. Or I'll call on you. You've already answered some stuff. Costello, what's the other interval?
Like which interval?
Where's the other increasing interval on this graph?
Negative. What point is that? No, it's 0.733. From 1.5 into infinity.
Oh, okay. So you were going from here.
0.5 negative whatever that is.
Technically, the increasing interval starts down here, right?
Yeah.
Okay, so the x-coordinate of this point is what?
I don't know.
You didn't write it down?
I didn't.
Oh, you should. Okay. That point had an x value of 0.733. So this interval is going to go from 0.733 to infinity. All right, so decreasing then. That decreasing interval is right in between the two increasing intervals, right? So if you have these two answers, you can easily come up with this one. So anyone who would like to share that with us would be welcome. Okay, Jason, go ahead. So remember, we only need the x, though, to write the interval. So it starts at negative 1.289, okay? And finishes up where? Yep. And that would be our one decreasing interval for this one. Okay, make sense? We can do that? Perfect, okay. So that's doing it without a calculator, with a graph, and then with a calculator with its graph. So, all right, I just got two other things I need to talk about, and I'm done. Shh. Okay. The location principle is, I guess, sort of kind of related to this stuff. It's talking about specifically x-intercepts, though. Okay, so maybe we could have talked about this one in some of the other sections when we were trying to find roots and all that. But the major difference with this thing is, this is showing you a way that you can approximate where a root is if you don't have an equation or a graph to look at. Okay, if you have data instead. So if no graph, no equation, just data. And by data, I mean like if you had like an XY chart with numbers in it or something. Okay? So, in the quote-unquote real world, when we're talking about trying to figure out zeros and that sort of thing, and there are statisticians and people like that do this stuff all the time, they're using data. 9 times out of 10, what you have to work with is just a set of numbers. Okay, we've got data coming out our ears now with computers and everything. So I'm just making up some fictitious numbers here, but this could apply to whatever. let's say that I don't know the equation, I don't know what the graph looks like, but I have this data that I've collected. And so I have some x values 0 through 6. And I'm going to have some y values that go with it. Okay? Let's say my y values go -3, -1, 2, 4, 1, -2, -7. Okay. Some function that these points are all sitting on. It's some mystery function. I don't know what it is. Okay? But I'd like to know where the zeros are of that particular function. Okay? So, just by looking at the numbers, can anybody tell me where those zeros would have to fall? Not exactly at -3.
Oh, between 1 and 2. No.
Mm-hmm.
Yeah.
Mm-hmm.
And in between 4 and 5. Wow, so smart.
All right, please elaborate. How do you know that those are where they're going to be between those? You don't need to come up to do that.
No.
Just explain.
Because between -1 and 2,
Uh-huh.
the y,
Yep.
that means it goes by 0.
Right. Exactly. Between -1 and 2, it's going to have to pass through 0, right?
Yeah.
If this thing's a polynomial, it's going to be all nice and connected. So to switch from negative to positive, there has to be a 0 somewhere in there, right? So on the x-axis, then, that means somewhere between 1 and 2 is where this thing hits 0, right? And the other one, because it switches signs back to negative between 4 and 5, that means there has to be another 0 somewhere else between 4 and 5. Okay? But because it's just data, that's as much as I know. I can't do anything more than that. I can't then go and pinpoint exactly where they are because I don't have an equation to work with. I don't have a complete graph to look at. I just have these numbers.
You can, if you make like a pattern between those numbers, you can...
One thing that you could do is you could take this data and try and do like a polynomial of best fit kind of a thing. You guys remember doing that with lines and quadratics? We used a little scatter plot on our calculator, and we did like linear regressions and quadratic regressions and all of that jazz. You could come up with one, but we don't know for sure that that's the exact function that's being used here, but that would just be one that would approximate it pretty well. So we could use that to make a good estimate, but again, we're not 100% sure that that's what it would have been. So for now, the only thing that we know for sure is that an x-intercept or root is between 1 and 2, at least for that. And then also here, we know there's an x-intercept or root is between 4 and 5. So 1 point something and 4 point something is going to have to produce a root for us here. That's all the location principle says. Okay, it doesn't give us any more information than that. Okay, but it's just a way to at least know something about where a root's going to be if you just have data to work with. Okay, and usually, like I said, statisticians, that sort of thing, if they're looking for zeros, or if they're looking for patterns in the data, they'll be scanning stuff and looking to see, as I go, where do I have sign changes? Right? Where does it switch from negative to positive or positive to negative? And those are going to be points of interest that they're going to be analyzing and that sort of thing. So this is just one part of that. So, okay, last thing I need to talk about with you guys, kind of switching gears here again, are even and odd functions. Not to be confused with even and odd degree. Very easy to confuse the two things. We've talked about even versus odd degrees of polynomials, and that's pretty easy to determine if you have an equation, right? You just look at the degree. If it's an even number, it's an even degree. If it's an odd number, it's an odd degree. But even and odd functions are something different. Okay? I'm going to give you a few functions here to look at, some graphs of them. And these are all even. And I want to see if you can tell me, what do they all have in common?
They both have
I haven't done anything yet. Okay. So jot those down real quick. And think about it. What do they all have in common? Mr. Brecking. Okay, so their end behavior is still the same on both ends. Okay, which is something that we said even degreed polynomials do as well, right? Okay, but there's more than just that going on here too. What else do you see, Bittner? Mm-hmm. They're all above the x-axis? Okay. Yeah, that I did by mistake. It doesn't have to be that way. But good catch. You're true. That is true. Anything else you guys are seeing? Liz?
Equivalent, like all the,
What do you mean by that exactly?
like from one interval to the next, like they're all equivalent.
So I think someone up here said the word. They're symmetrical. You guys remember that from geometry? What a line of symmetry is? A line of symmetry is a line that comes through and creates a line of reflection where if you reflect the thing over that line, it's exactly where it started. It looks exactly the same. Each one of these, the y-axis, is serving as a line of symmetry. That's how you know you have an even function. Question? W, V, and M. Yeah. W, V, and M are all even function graph letters? I don't know. Anyway, so here's the definition for even functions. Okay, so the function has the y-axis as a line of symmetry. Okay, that's important. It has to be the y-axis too. Okay, it can't just be some other random spot. So, like, for example, that little guy, that's a parabola. That's a parabola, and it has a line of symmetry that I could make right here, but it's not the y-axis, so that's not an even function. You guys see the difference? So this one, not even. Okay? If I shifted that thing over a little bit, yes, it is. But it has to be symmetric around the y-axis for it to be even. Okay? So if you can graph a particular function and take a look, if you see this kind of happening, then you can say, okay, I know that's an even function. All right? Now, how does an even function get its name? It is really closely related to what we were talking about with all this even and odd degree business. In fact, that's how they came up with it. If you just graph things like x squared, x to the fourth, x to the sixth, the graphs of these things are all even. So x squared looks like a parabola. X to the fourth kind of flattens out. X to the sixth like really flattens out. Okay? Each one of those is exhibiting this property, right? Yeah. Okay? Now, if I take any one of those, x squared, x to the fourth, x to the sixth, and I do some transformation to it, then it's not even anymore. Unless all I do is move it up or down, then it is. But if it's left or right, if I stretch it in some other way or flip it around and then move it, it's not necessarily going to be even anymore. But this is where the even function gets its name from. Because even polynomials, when they're in their most basic form, have this property. Okay? A stretch or a shrink wouldn't do it either, no. Real quick, I'm going to give you some odd functions to take a look at and see if you can tell me what's going on. We're almost done, I promise. No, because we're just about done.
That's not symmetrical.
Not symmetrical.
That's not symmetrical. Wait, maybe it is.
Okay. Anybody see what's going on with these three?
They're like flipping upside down and they're different quadrants.
The line is
Yeah.
on the y-axis.
You know what? There is no line of symmetry with these.
Got it.
What is it?
They rotate 180 degrees on top of each other.
Boom. Got it. Each one of these. Now, I heard someone else say it, I think, Gray, I think you said it, where it flips down and then it's symmetrical. Both are the same thing. If you take each one of these and you take half of it and flip it up or flip it down, either way, then it becomes an even function, right? This one, you flip this piece up, and then it's going to be this like V-looking thing. This one, you flip it up, it's got that, both with that line of reflection. This one, you flip it around, it's going to look the same as the other one. You can think about it that way if you want, but I think probably the easier way to look at it is rotation. Each one of these has a point of rotation right at the origin. And if you spin it 180 degrees, it should land right on top of itself again. Okay? It's an easy way to identify an odd function by graphing the thing. Okay? So, here's what we got for odd. The function has rotation symmetry. That's how we say that. Around the origin. So think about each one of these functions is like a spinner, and the center of that spinner is at the origin. If I can spin it 180 degrees, I'm going to put that on there too. If I can spin it 180 degrees, then it's odd. And get it to look exactly the same, and it's odd. Okay? All right, so that's even and odd. That's all I got. So you guys can get going on some homework here.